Hello everybody, I've just repaired this CTEK. It's just charged the battery, if you can see that. The lights aren't very bright on this one. We'll see them now. Yeah, so I've just repaired this and it's been quite a marathon. It's a blow-by-blow repair, it takes a couple of hours. Might be too boring, let me know what you think. But it is detailed with circuit diagrams, so yeah, without further ado. Actually, this was sent in by a YouTuber about November, so yeah, it's a bit overdue. So yeah, without further ado, let's get on with it and let's get on with the repair. Hope you enjoy it. Look what we've got. Sent in by a YouTuber, a CTEK 12 volt only, pressy button, motorcycle, star, standby, alarm, battery half full, battery full. Multi xs3600. The XS stands for excess pricing, so yeah, think of a price, think of a reasonable margin, and then treble it and then sell it. Paint it silver, smoke and mirrors, and then a few extra connectors, and you've got yourself a major winning product as far as the fiscal arrangements, not the technical arrangements, are concerned. So here it is anyway. Look, so you can have a look at that freeze frame, have a shufty. Developed in Sweden, made in the deepest and darkest regions of China. You notice it's supposed to say where it's manufactured and it doesn't. So that's not really within the EU rules, is it? Got to have country of manufacture on there, boys. It's a bit loose. Anyway, so it's not working. It's dead as a dodo. And let's just whip the back off. I've not seen one of these before, so I'm kind of keen to see what's inside, you know. I like looking inside things. It's much easier than designing them, I'm telling you that. Right, okay. Although I am working on a battery charger at the moment, you are going to be impressed. I'm impressed and I designed it. Right, so yeah, recycling mark, the type of battery, polycarbonate, so it has got the recycle marks in it. Well done, you Swedish chappies. So yeah, that's the Lidl now. You do not have these recycling marks, which makes them non-CE approved technically. So I didn't know they did their CE technical evaluation for Lidl and Aldi, but if you're watching, boys, I'm available. Right, okay. Oh look, it looks quite nice, doesn't it? Look at that. Blue. Metal. There's the output filter that was missing on that one we were messing about with the other day. There's the input filter under there, we were messing about with the one the other day. So yeah, it looks like a properly engineered. There's your two linking capacitors for class Y. They've actually put two in series with like belt and braces, so well done, super safe, excellent engineering. Looks better made than the last CTEK one we opened up. Do you remember that one? It was the MX 5.0, was it MXS 5.0? You know the one. There's a playlist on the channel, you can have a look. So that's we can't get this out, unfortunately. It's a captive board. So anyway, let's have a look at that. That looks alright, doesn't it? That looks okay. Lots of that horrible bloody glue everywhere, but I'm guessing that's a what is that in there? Thermal cutout, do you think? Who can say? It seems to be strapped on top of a whatever that component, a capacitor. So there's a nice big output choke, look, and that's going to filter the output stuff and keep it within the bounds of CE. I have no doubt this is probably CE approved, because I think the Swedes take everything more seriously than us. Apart from alcoholism, and I do understand they like their juice, their sauce. Right, so what have we got? We've got all the, God, what are horrible electronics at this end, look. Might be designed in Sweden, but I mean, on the secondary side, what could possibly need that many components for what this does? You think the micro would have the intelligence and you just need a comparator, then there's some sort of current and voltage drive circuit for the power supply. So it's probably, but to be fair, it's probably an old generation of power supply, so let's not criticise them for that. It is an FR4 PCB, so this one has got a proper glass fibre PCB in it, not that horrible compressed cardboard stroke epoxy Paxilin stuff where the, you know, you look at it wrongly and the tracks come off. Right, so let's go and have a closer look. Right, so you can see this is the valley of separation between the voltage power supply, the mains power supply, and the DC side where all the magic happens. And this is the switch mode power supply. Minimalist design by the look of it. But yeah, let's have a close look. So I'm going to zoom in on that bit, put that in the middle, and I'm going to zoom in for you. Right, okay, so what we got? Which management chip is that then? It's a pokey thing here. Get kebabs from the shop down the road. The sticks are really good. Good old sticks these are. Could do your knitting with these. Right, what we've got? We've got HEF4069 UB HEF4069 4069. That's a hex inverter. What? What have they done? I'm just going to check that as a hex inverter. Hold on a minute. Oh dear. Yep. It's just an inverter. Is it a Schottky inverter? Let's look at the data sheet. Not working. Go to RS. Something wrong with the Farnell data sheets, don't always open up, whereas the RS ones do. So if you're watching Farnell, fix your data sheet formats, whatever's broken about them, because they don't work half the time. Whatever's processing the data in data sheets into data sheets is not working. Shame on you. There it is. Bum, 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 plebeu. Yeah, it's not general purpose hex unbuffered inverter. Each inverter has a single stage, 3 to 15 volt power supply, and what the hell have they done? I can see on radio spares that this chip is a, yeah, this is literally a 15-cent chip. If you buy a reel of 5,000 of these, you've got 15 cents instead of a 45 to 50 cents for a proper PWM switch mode power supply management chip, right? So look, and look, it's got it's had an incident has happened. It is no more. Something went wrong and blew its guts out. Look, there you go. You can see there's a fissure in there, just there. Fissure. And oh god, look at this. It's a disaster zone. A transistor, a resistor, a resistor, a resistor, a resistor, choke or resistor possibly blown. Goodness knows about these. So clearly what's happened is the drive from the FET, which is this track here, that's the gate, source, drain, insulation has broken down. The full charge from the mains capacitor, the smoothing B plus 350 volt capacitor, has come down that line into this chip and just bloody destroyed everything. Now I'm quite keen to fix this for the chappie, because I would like to see how this works, because this is just a hex inverter, so clearly they've made an oscillator down this end out of a few of the gates, and can you see they're all paralleled up the gates to get more drive for the output. So that one, pins 7 and 9, pin 7 and 9, 7 and 9, that's not 7 and 9, is it? That's 8 and 10. Yeah, so all that, they're all paralleled up, so the drive for the FET is 3 of these gates all parallel together to give extra drive oomph to drive the FET. Doesn't look like there's any conditioning electronics in between. Anyway, the FET's gone and blown this up, okay? So if you've got one of these, model number multi xs3600, because I'm just thinking I can't really do very much with this, because I could try and work out what these values are, but honestly, if you've got one of these that's working or undestroyed, or I'll do you a deal if you've got a broken one, but you can see what these values are on here. And the ident on that transistor, I can probably guess that one, but anyway, that would be useful on this one. You can see they're all fried. All the low value resistors have all been fried up. It's quite an event, eh? Yeah. So if you could send me a picture of basically that area there, all those components, that I could see what these values are on R102, R100, R21, C9. No, it's not C9, that's R7, that's gone. Look at that. Look. R5, T2, probably the ident on T2 is important. R102, R100. I know what that is, obviously. Then I can fix this one for this tubey chap, and fix yours too. So if you've got one of these, as I say, 3600, whip the back off for me, and just take a picture of that bit and put it back together carefully. And if yours is broken but you can read all that, then send it to me and I'll fix it if you tell me what these values are. So it's a shout out to give me those values, and I'll repair this and do a repair video on it. Okay, so hope you enjoyed watching that, and hope to hear from you soon. Okay everyone, we've got this CTEK multi xs3600. You saw it in the other video. Bob, thanks Bob for sending the list in. A YouTube viewer sent me a list of what the components are, and so we can just quickly get in there and change them. What I'm going to do is to pull off all the older components and then poke around on the things that I suspect, like these diodes and these transistors. And this transistor is not obviously blown, but we can meter those out, and I'll explain that as I go along. You can see that all of these have been fixed down. This has been flow soldered in the wave bath. You can tell by the pad layout, and also the fact that it's got these red blobs of epoxy. The components are epoxied onto the board before they put it through the wave solder, which it goes through the wave solder that way up over a breaking, cresting wave of molten solder, presumably unleaded. Right, so before we do any more, let's just whip these components off. So Bob's given me a list. I've written them down from the email he sent me. Well, you can't see that. Bob's given me a list, and we know what's what now. So we're going to do this with a soldering iron. I could do it with a hot air gun, but presumably you'll want to see it done with a soldering iron, because you might not have a hot air gun. I'm trying to encourage everyone to rescue their kit. Okay, so you need a pair of tweezers, a soldering iron set to about 400, and some flux. I use the Kingbo RMA 218. Allegedly not very good for your health, so do it in a well ventilated room, or don't do it at all. I've got some multi-core 5-core leaded, so I'm just going to dilute the stuff with leaded and see. We'll see. Oh, there's some tweezers. There's some tweezers. Yeah, I might need to pick these off with the tweezers, which is going to make it awkward. We'll see, shall we? So let's start with the chip. Let's get some heat into her anyway. Let's start with the chip. So we're just going to flood this with solder. I could use the hot air gun, as I say, but where's the fun in that? I've got my red wine. This is an evening job. Smoky. Smoke and alcohol, lovely. Alright, so let's see if we can just pick the corner of that up. So it's a bit like plate spinning, but it's stuck down. There you go. So she's off. Okay. There we are. Clean your tip. No one likes a dirty tip. So what next? R102 is blown. We can see, we went through this last time, they're physically blown. You can see there's no point in actually even measuring them. Give them a tweak, get them off. R100 is blown, R100. Let's get rid of that. Get rid of that, and that. Lovely. R5 is definitely blown. Get both ends molten and give it a bit of a tweak like that, just to break the epoxy off. There we are. R5 is gone off. What else have we got? This one here, which is R7 is blown. It's getting smoky in here now, boys and girls. R7. Oh, you can't fucking see, can you? Can you? R7 is gone. Not sure about R21. We'll check that. Any others? Any more? Yeah, this transistor. Transistor 2 down the bottom here. Definitely a goner, if you ask me. Let's give that a bit more brightness. There we are. Hold it down, 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 hold it down. Come on, get a tweak. There, she's off. Anything else for anything else that looks obviously destroyed? Right, nothing obviously destroyed. Nothing obviously destroyed. Can you see anything else? Bear in mind, I mean, that's 101, so that's 100 ohms, so that could be destroyed. The voltage can only force its way through because obviously everyone knows current, it's the voltage is the cause of current flow, and the resistance to current flow is the resistance to current flow is resistance. Therefore, the higher resistors won't be blown up. So anything above a couple of K on here should have survived a quick encounter with the B plus running at about 320 odd volts usually. Yeah, so I think what we'll do, we'll just give her a quick scrub off. A bit of a scrubber. Talking of scrubbers, my tea's ready. Yeah, don't want to get my new desk dirty. Ooh, there she is. So I'm going to do a bit of a clean so we can operate. The flux will stop the meter probes making contact, and I'll have all sorts of trouble, so let's just clean it while we can. Alright, okay. Now, just a quick recap on this, just in case you don't know about this, is that if you've got an NPN transistor, so I'll draw an NPN transistor here, collector, base, emitter. Now you know that's that, and it's actually made of a sandwich of material, and it's a P material, and then sandwich in the middle of the gate, which is very, very small. So that will be N, P, and N. Okay. So the equivalent circuit of this, when you're testing with a meter, is if you put the red lead on the base. Yeah. So you put red on there from your diode continuity mode meter. You put the red lead on there. Then between here, you've got equivalent of a diode going that way. Well, if it's not powered up, a diode there, and a diode there. Okay. So by checking that if you put your red lead on there and make sure you've got like 0.7 volts, assuming a silicon transistor, 0.6, 0.7 volts, you've got the normal forward diode voltage drop on your meter, and then you put the meter on the emitter, you should have the same, around about 0.6, 0.7 volts. Then you swap over and put your black lead on there, you should get no continuity, or certainly a voltage higher than the 0.7, which indicates, if this is in circuit, say there's biasing resistors and things in here, like you know, alternative current paths, you can draw a very strong inference or conclusion as to whether the transistor is blown or not. So let's check a few of these transistors and see what they are. So I've got my meter on diode forward voltage drop continuity. So just to recap, this meter will display, it puts about 3 volts across these probes, and when you connect it up to the circuit, it will read the voltage which is dropping across the component. So bear in mind, our resistor will give you a drop as well, but a semiconductor, silicon semiconductor, should give you 0.7, alright? So let's just check a few of these components up this end of the circuit. I can just get that in there. Can we display that on that? Can I put that on there? Can you see it even? Rubbish, you know, I want to swap meters, hold on. Okay everyone, we'll just carry on with this multi xs3600 battery charger, which was sent in by a YouTuber. Got some wine. Nice glass of wine. Got my meters and the camera set up, so let's roll it, shall we? Yeah, so actually what I have got on this thing, which you probably haven't seen me do before, is a circuit diagram, which was a link was sent to me by a very handy viewer actually, because I was going through this thing, doing the normal thing of trying to sort out what was what and just reverse engineering it in a very sort of crude and rough and ready way, and yeah, this circuit diagram turned up. Now it's not exactly the same as the circuit on here, But I thought I would just run through the circuit diagram with you, and then you can have a look and see, follow it through on here. But there are some differences, but they're minor. But it's a very, very cheap power supply design. It's quite audacious, really, and impressive in some ways, but then in other ways, I'm not surprised it's gone wrong. Fruity red. All right. So, looking at this circuit diagram up here on the screen, it's the CTEK xs3600 primary section. So I've only got the circuit diagram for the primary section, i.e. the mains power supply section that provides the DC charge voltage to the lower side, but you can't have everything, hey. And you can't see much of it at the moment, so I'm going to blow it up and go through. You can see where my mouse is at the moment, there, up there, mains input, rectification, smoothing, filtering, more filtering, and then this is the low voltage DC series regulated linear power supply for the voltage to supply this really crude chip down here. It is a hex unbuffered inverter CMOS chip, and you can see they've made an oscillator out of the first 3 gates, and then they use the last 3 gates parallel together to increase the drive for the FET here. Snubber circuit up here, transformer there, current sensing circuit there, combined with the demand side drive via the opto isolator to this transistor to turn the output on and off to get the right voltage or current coming out the secondary, and then an over temperature circuit here and a little transistor here to invert the sense of this. So if I just blow this up, is that big enough? It's probably not big enough, is it? Okay, so we're in the top left hand side of the circuit diagram at the moment. There aren't 2 fuses, there's just one, only one fuse. So the 47N is there, filtering, that stops AC noise, switching noise from the power supply going back and radiating at the cable, causing MC issues and interfering with the equipment. Bridge rectifier diodes, 4007 1 amp 1000 volt diodes, silicon, very robust diodes, actually very reliable and very old. You know, they've been around for at least 30 years, I think, 25 years. 22 microfarad 400 volt capacitor, that's your main smoothing capacitor. Notice they call this ground, which isn't ground at all, it should be AC 0 volts. But hey, ground will do. And then if we go over to here, so we're going right now. So at this point here, actually, just mention this is your AC mains coming in, and it's rectified. And if you've got, for example, in the UK, we've got 240 volts AC coming in, this will be sitting, whilst rectified and smoothed out, you get about a 330 volt-ish DC on this V plus up here, all right? So it's really a 300 volt DC power supply direct from the mains, rectified and referenced to the mains. It's not isolated, obviously. So if we scoot along a little bit, right, so here in the, this is the 300 volt rail, this rail coming across the top is the 300 volt rail. And then you can see what you've got here is, it says, no prizes for guessing this one. VCC power supply 11.4 volts. So this has got an 11.4 volt DC supply, which is derived from the 330 volt supply to drive this unbuffered 6-gate inverter chip, okay, CMOS inverter chip. Now you can see that it would be nicer if this was drawn a little bit more friendly fashion, but what you've got here is a 470k resistor. Of course that's going to give you 330 over 470k, so 330 over 470,000 milliamps or amps coming down here. So a very small current coming down here to bias this BZX84C12, which is a 300 milliwatt Zener diode, 12 volts. So current comes down here and drives this point up to nominal 12 volts, limited and clamped by the Zener. Notice there's no capacitor across there. You'd often expect a small decoupling capacitor across the Zener, but they think it's not necessary, not being bothered with. And then you've got the main source of the current for the supply for the chip comes down this 82k 1% resistor. Okay, now the 82k is there to limit the actual dissipation in the transistor there, because this transistor is arranged in an emitter follower arrangement. So
the emitter will always be roughly about 0.6 volts lower than the 12 volt, hence the 11.4 volts there, because the actual the base emitter junction will be about 0.6 when it's normal DC biasing and it's switched on, hence giving you 11.4. okay, now what they've also done is they've put a current sink to here, so this resistor here is bypassing the transistor. Okay, so if you take the lowest case current that's required by VCC through that 120 ohm resistor, then the 120k there is literally just to provide a bypass to reduce the dissipation of this transistor. Clearly you're going to have 100 volts or something across this transistor. You want to keep the voltage across this transistor as small as you can to minimize the dissipation, but you also want to have the transistor have enough headroom to demand a bit of extra current by pulling more current through the resistor and feeding it through to this point here. So you've got this potential divider plus the augmented side by the transistor with a 1k resistor in its emitter going to the power supply. Right, now onto this supply as well, I've got a 120 ohm resistor into the supply to the chip, just a filter basically, and a 100 nanofarad noise filter capacitor. So quite often a simple resistor in the power supply will filter out a lot of the HF noise due to the capacitance of the rest of the circuitry. Okay, so that is a series linear, roughly regulated low voltage DC power supply creating 11.4 volts from the 300 volt line running on 220 volts AC. Now what I couldn't quite work out, what was the point of this diode here? That wouldn't normally be there, that diode, and I think that diode is there so that if, yeah, I've worked out what the diode's for now. If this transistor turns off, then potentially, because there's a potential divider here, this could go up to 300 volts. So this diode is simply a clamping diode to clamp the emitter to within, well, it would be if this suddenly switched off the transistor and there was no load here, then you would have the current flowing down through that resistor from the 300 volt rail. The transistor collector's not conducting through there, and this would tend to go higher and higher. And what it doesn't do that, because there's a 1k here feeding down through that diode, clamping it down through the Zener. So that D14 is a clamping diode. I'm glad I sorted that out. It took me a second there. So 11.4 supply going in down to power this circuitry down here. All right, I think I'm all right on that one. Right, also if I 300 volt line coming down through a 2meg2 resistor through an 8k2 to 0 volts or AC 0 volts, BC486846 general purpose NPN transistor used to bias this oscillator. Okay, so this will not turn on and bias this oscillator to make it start switching for the power supply until there's significant V plus there. It's to stop the power supply starting up before the voltage on the smoothing capacitor is high enough. You don't want this to start or misfire or do something strange, because most likely it will blow the FET. You need to start switching cleanly when it's ready to rock and roll and everything's ready to go. Okay, so more biasing here, 1 meg ohm resistor biasing pin 1 of this inverter. And if you look down here, there is a transistor down here, the BC846 transistor 2, and if you turn that transistor on, it clamps this end of the input of the oscillator and shuts the oscillator down. Okay, so this transistor switched on will shut the oscillator down. This transistor not switched on will not allow the oscillator to run because there's not enough bias on it. And you know, with any oscillator you need gain, and also you need phase difference, and you get the phase difference between these two stages with the capacitor and the resistor, and you end up with an oscillator running probably, difficult to say actually because it's not a straightforward time constant because of the dynamics of these devices, but it's probably about 50 kilohertz I should think. And then at the end of this one, at the end of this oscillator stage, this is a part that drives the power supply. We'll talk about the shutdown of the power supply and the regulation in a moment. Is what we have here is just 3 gates all paralleled up to, and the reason they're paralleled up is to increase, you get 3 times the current source capacity of the output and 3 times the current sink capacity of the output, driving straight into unconditioned, unprotected into the gate of this IRF 830 NMOS power FET. And we'll look at the switching side at the moment. Remember that this FET is switching at something like 50 kilohertz. Now, to control the power supply so it doesn't go wild, you've got three inputs here, isn't there? Look, if I move this across, remember this line here going to the base of that transistor. If this line is pulled high, it will turn the transistor on and stop the oscillator, stop the power supply, shut down. And bear in mind, this is happening on the demand side. This could be happening 50 times a second. It's teetering on a knife edge, and there's just little bursts of pulse coming out of here to keep the output capacitor charged. And it's particularly under load. It will only be just on for a few cycles, every 50 cycles or something like that, just enough to pump a bit more charge through to the secondary side to keep the reservoir and the voltage on the secondary side charged up and at the correct voltage if there's not much current being taken. So here's the demand. So this LED here, this LED and this fiber optic will be driven from the secondary side. There's 2000 volts isolation across this device. This is the DC side accessible to the user, the clamps, the battery, and so on. This is the main side, reference to the mains, which if you touched it and touched ground, you'd get a shock. All right. So yeah, across here you've got a voltage comparator somewhere in the secondary side. When this gets up to voltage on the secondary side, it turns this LED on, switches this transistor on via the infrared optically coupled diode. It's really a photodiode actually, not a transistor, but I suppose you could call it that. But it's the photons are acting on the base of the transistor, the base area, making it conduct. So when it's up to voltage, the comparator circuit on the secondary side puts some power through this LED, switches that transistor on, pulls this point high, and then stops the power supply primary section producing any more power until this LED goes out. So that's one method of controlling it. The second method here, the second method is this over temperature detector. Again, we've got VCC, which is the positive power supply for the chip, 11.4 volts. PNP transistor, some biasing, a biasing resistor, and a 470k NTC thermistor. Okay, that's the thermistor that detects actual ambient temperature inside the unit is too high. It starts to go low in voltage, pulls this point down, switches on the transistor then passes this point high, which turns on this transistor and stops the oscillator. All right, and the third method of this control is the current sensing. Current sensing here is all in the source of the FET. You've got a 1 ohm and a 2.7 ohm resistor, and they're obviously in there to get a nominal lower than 1 ohm value, the right value to actually make or set the unit so that when you have a too high a current going through this FET, i.e. in the primary, so there's a short on the secondary side, bad overcurrent condition, much more current flowing down through the FET, through the primary of the transformer up here. This is the primary of the transformer, generating a high potential across these set resistors, and at a certain current, which is controllable by the values of these set resistors, bear in mind they're in parallel, you get a pulse. Every time this switches, you'll get a pulse, and the height of the pulse here at this point will depend on the current flowing down through the FET. In an overcurrent situation, it goes too high, feeds through this 100 ohm resistor and a 470 picofarad capacitor, so you can see there is a time constant there to filter it slightly, and when it rises above a certain amount, it's coupled through this 4N7 on every cycle, and the 4N7 then switches on this transistor, stops the oscillator. So in fact, if you've got a serious overcurrent condition, as soon as you start to drive this FET and the current goes too high, voltage is generated, fed through to here, goes through the AC coupling to this point here, turns on the transistor and kills the oscillator. All right, so it stops your FET being blown up by an overcurrent situation. Now if we scroll up FET, then you're at the primary of your transformer, and I'm not really sure what this C1, it looks like this C1 is coupled to a screen inside the transformer. Never noticed that before. It's an electrostatic screen, so it won't be magnetically coupled. It might just be a screen in the transformer. Interesting one, not sure. Anyone know? Leave a comment down below. I'd be interested to know. And then up here you've got your snubber circuit. And across the primary of the transformer, it's usually you've got a resistor, a capacitor, another series resistor, and a diode. And this one says 1N4007, which it definitely isn't. And someone's put BA159. 1N4007 is just a plain old silicon diode. And this is a BA159 1 amp fast recovery diode, something like 130 nanoseconds, I think. Look that up, I think, in a minute. But anyway, so this, when you disconnect, when you switch off, this will go pinging out high like it does in catcher ignition circuit. You don't want that. So you conduct that and damp that overvoltage spike back through this network in a time constant to actually keep the primary current flowing longer, improving the efficiency, and also preventing damage by a huge voltage spike on the FET. So what's gone wrong with this one? You saw the sorry old state that it's in at the moment, and what the problem is that problem on this one is that this FET gate has shorted out to the drain and source. And you can only assume that when they do go, they short across this junction here, because you get the full, don't forget, in a DC situation where you're not, the inductor is fully saturated, the transistor's been on for a while, you know, I'm talking about milliseconds, you've got full DC current going through basically a piece of copper wire, which is quite a chunky piece of copper wire in comparison. Comes down here, down through the FET, out through the gate, and then straight into these low voltage devices which are supposed to be running at 11.4 volts, and you suddenly dump rectified mains in. It's not going to end well. All right, so what do we look for when we look? We saw the components which were burnt out, but obviously this chip is going to be completely burnt. Quite possibly this opto-isolator may be damaged. This opto-isolator usually goes back through a network to somewhere on a switch mode power supply PWM controller chip, but clearly this one's right in the firing line. So this could be damaged, this transistor, even though when it's biased with the light, the optically biased on, it is, you know, you can look at this as a constant current device. You wouldn't be able to drive a huge current through this, but then again, I don't think the voltage rating of this transistor is anything above 30-40 volts or something like that. And if 300 has come down here, this is likely to be gone, so we're going to have to test that first on the transistor side, on the main side of that opto-isolator. Now coming back through here, we've got anything. I mean, you can think of this whole chip now as a shorting link. You know, probably anywhere, any pin, 300 volts could have appeared. All right, so the 1 mega ohm resistor is not going to be bothered. The 121k resistor is not going to be bothered, because you won't be able to drive enough current through to do anything catastrophic to this transistor. Probably we will check it, but I will suspect that that's not blown. All right. Remember, lower value resistors, higher voltage, you can drive much more power through them, current through them, i.e. power, and then they will go pop. So VCC here, we had 300 volts come down there. Well, we got 1k and 100k, so that's not enough current to blow this chain up. But this 300 volts through this 1k and 470k, probably not either. It is an NTC, so if this got hot, resistance could come down, way down, and then damage this transistor, a high fault current going through there. So we're going to check this transistor, but I'm hoping that this is all right. We will check this 100 ohm, because it is a possibility the transistor's gone. It's still got to go through 100k to get to ground, doesn't it? So unless the NTC went short, we're probably okay, I think. It could, 300 volts here could destroy this transistor through over voltage, couldn't it? It could have damaged it if it's a 40 volt device, so 300 volts across the emitter collector junction. That's not going to be good, albeit it not very high current, but we need to check that as well. BC846. Large current comes down here through the FET. Quite often on power supplies, the current sense resistor is blown. Not every time, but I've seen quite a few. And if these 1 ohm and the 2.7 ohm has been blown open circuit, then you've got 100 ohms, which the mains would come down. through to this capacitor. So this capacitor could have been over voltaged. It might only be, you know, this working voltage of here is just going to be a volt or something to bias that transistor on, driven through that capacitor. So this 4N7 cap could be blown. To check that as well. And what else have we got here that could get fried up down this end of the circuit? No, they're all high impedance. So switching back up here momentarily. Yeah, so in this circuit, again, this circuit could be, what we've got is 11.4. We've got 300 volts coming back through this resistor. So this resistor could be blown. That 1K could be blown. The BAS16 could be blown. And the Zener could be blown. And possibly even the transistor, because we're reverse biasing the emitter base junction quite massively if we get a large voltage down here. So this FFMT 458, 400 volt SOT23, I think, small transistor, but 400 volt could be damaged as well because the emitter base.
Alright, so let's have a look at this board. We have zoomed in under the spotlight is T4, the series NPN voltage regulator that provides 11.5 volts to run the actual low voltage electronics on the main side of the power supply. You can see from the diagram it is an NPN transistor, and on these packages, generally speaking, if the leg is facing away from you, the base is on the left, the emitter is on the right, and the collector is the top one, right? So you should be able to check the NPN transistor, NPN junction. So there's two NP junctions, i.e. two silicon diodes in there, effective. Right, so just checking the base collector junction, you should get a diode there. There you go, not making contact, 692 millivolts, there's a junction there. There's a junction there, and if you swap those over there, you should get overload, which you do, so that is not shorted and it's not doing anything strange. And if we meter there this way round, so we're reversing the probe, so we've got the black probe on the base, we also get 648 millivolts, which is strange. On a transistor you wouldn't normally expect that, but if you look at the circuit diagram you can see why. Can you see D14? So D14 is probably good too, so that survived, that's nice. So T4 is good, tick T4 off. Now coming back down to the other components we said we'd check. Let's just move this around a bit so you can get a view of where we need to be looking. Okay, so we're looking at the back of the FET at the moment. This is the main switching FET, this one here. It is part number on the IRF830 FET, and we've got the source goes to 0 volts, which is that must be the source, mustn't it? This is the drive for the gate. They're coming from the 3 gates on the IC10, which is the inverter chip. There's the drain, which goes to the primary of the transformer and the snubber circuit, so there's a snubber diode behind there probably. And so this is what's broken down. We've had a short between here and here and here and here. Something inside the FET has broken down. The FET has gone poof. We've had a catastrophic overcurrent. And what we've got down here, if you can see this thick track going down to here, these are these two resistors, R9 and R66, and they're on the other side of the board behind the metalwork, I think. Yeah, that must be the other end of them there, look. Can you see that? So there's the two resistors in parallel, and that's the current sense resistor. So let's just check across there, and it should be a short. It's not. So those two resistors have been blown totally open circuit, without question. That's the problem with that. So we've got to reinstate those two resistors. So what have we got? R9 and R66 are shot, alright? And then you can see the track goes down. This is the sense track that goes down to here, which goes to C11, it should, according to the diagram. Can you see C11 down there? Let's just move that over slightly. Can't see C11 at the moment. There it is. There's C11. So let's see if C11 is shorted. No, it looks like C11 has survived, okay. So the main catastrophic, when let's go back up to here. Should I zoom out slightly here? Yeah, so when these two resistors let go, so sequence of events, okay, the FET goes short. Momentarily a large current comes from the mains power supply before the fuse blows through these resistors. These resistors stand up to it for a second, overheat, go pop, open circuit. Then suddenly you've got 300 volts, and now the FET isn't connected to ground or not AC 0 volts. There's no path to ground for the current, so the current then comes through the shorted FET, down through the FET drive, into this chip and out all over the place, as I explained before. So that's what's happened. And you can see that before we went through, didn't we, and we just, the obviously burnt components we've already removed, right? But we have got T10 down here, which is the over temperature PNP transistor. So again, we've got, this time it's PNP, so there should be a junction. You can see, here's the transistor there. There should be a junction between, that's the base, that's the collector. With the black probe on the base this time, because it's a PNP transistor, we should be able to see a junction. And we've got 194 millivolts, which does not look promising. Okay, let's just check that junction around the other way. (194 millivolts) again. So to me it looks like that transistor has gone. Let's just check the base emitter voltage. Yeah, dead short on there. So there's no measurable junctions on this transistor, and if you look in the circuit there's reasonably high impedances all around it, so that is dead. Now R102 is a 1K resistor which is in the emitter of that transistor. R102, can anyone see it? R102 is blown up already, look, so that gives an indication that that transistor has been overcurrented. Now I wonder what we've got on the NTC. The NTC must be mounted on the other side somewhere around where it can pick up some heat, so we'll have to track that down and check it in a minute. Now what else have we got up here? Alright, so if you look at the, going back to the components associated with T4, we have R21, okay, which is a 1K, and if we had an overcurrent situation on that, it should have, it may have blown, and look at it there, there's R21. If I just put this onto ohms now, we're set to ohms, and we're going to check out R21, which is that one there. It does look a bit splatty actually, look, can you see? R21 should be 1K. Just check the probes. Yeah. So R21 is open circuit too, so R21 needs changing. If I go back to diode continuity, do you remember we said we would check the Zener diode? Have a look on the diagram. Zener diode, and we should see with the red probe on the, also the black probe on the stripe end of the diode. This diode is actually a SOT23 package. It's this one, that one there, and you can see there's two connections to it. There's only two connections because it's Zener, and we've got the top one and the bottom one. So I'm guessing that that probably is the cathode. Let's see. Yeah, can you see we've got 0.758? So in the normal forward bias direction, the Zener diode will just read like a normal silicon diode. Slightly different voltages because they mess about with it to give it a low breakdown current. Sorry, low breakdown voltage. And yeah, what we got? We've got a diode junction that way, which is correct. You can see where my probes are at the moment. If we swap those over, it's open circuit. So that looks like that Zener diode has survived. And we know that D14 has survived because we already measured that when we checked the transistor. But we can check it again now, but we will see the junction of the transistor as well. So if we put the probes across here, we'll see 0.6 or 0.7. I can get it on there, that is. 0.6, get on there. 0.7, there it goes. That's the diode junction, and if I put it around the other way, we'll see the transistor junction of T4. Yeah, so that survived. T3, what's T3 do? Oh, T3 is the inhibitor transistor, isn't it? The one that switches off. Oh no, it's not. Yeah, T3 is the switch off transistor which is sensing the actual V plus, the high voltage supply, is in a suitable state for it to start up via R10. R10 won't be blown up, R12 won't be blown up because the impedance is too high, the resistance is too high, and R20 and R19 shouldn't have really blown up either because you can't force the current through those resistors. So incidentally, if a transistor junction or something breaks down to over voltage, it won't damage it unless there's a current there. If in an over voltage situation, providing it's not absolutely dramatic, it'll just go into effectively a Zener breakdown, start conducting, and if there's no dangerous currents around, that's when it conducts, it will overheat and burn and fuse the inside of the device. It'll just conduct. So with these high resistances around T3, I'd expect T3 to be okay. So let's just check T3. It is an NPN, so once more we want to put the positive lead on the base, which is there, and then we'll meter to here. You can see there's one junction, 773 millivolts. There's the other junction, and if we just swap that over, so put the black lead on the base, we've got nothing. So T3 has survived as predicted. Now, what else haven't we checked? Defaulting, we've done everything, haven't we? That is the demarcation line. If we just check the actual opto-isolator, which is across there, I think. Yeah, that's the pins of it. It's six pins, 3 pins there, 3 pins there. This is the photo transistor stroke photo diode of the opto-isolator. And if we just check that transistor within that package, right, it's it shows 3 legs coming out. It shows the base coming out. So one of these should be the base. I'm not sure which one is which. I can't see what's connected to where because it's on the other side of the board, I think. Or is that connected to there? Yeah, it is. So that one is connected to the end of C11. So that is the emitter. Alright, so that one's the emitter because it's connected to C11. Look at the diagram. The emitter is connected to the base of T2. So if we go to the base of T2, yeah, the base of T2, which is that one, should be connected to one of these pins. It's connected to that one there, which we thought was the... That's right, so that is the emitter. Look, there's the base of T2 is connected to the emitter of there, which is also connected to one of C11, see the diagram. So the other end of this thing is the collector, which should go to pins 8, 10 and 12, and the gate of the FET. Now the FET is still installed, so this will still be... I know those resistors have gone, haven't they? So it won't be shorted to ground because of the current sense resistor. So let's just try that and see if we can get a reading on this. Pin 8 of the chip. 1, 2, 3, 4, 5, 6, 7. Pin 8 of the chip should go through to the collector of this. Okay, so there's collector. Right, so now we know what pins they are. We've got the emitter, we've got the collector, and that's the base. Okay, and the transistor is denoted as a PNP. So if we put the meter probe on here, on the base, we've determined is the base, and check the emitter, there should be a transistor junction, and there isn't. And there should be a collector junction, and there isn't. Now the question is, would this appear to be a normal thing without any normal transistor, without any light shining on it? It's unusual that it's pin 5 and pin 4. So this divides 1, 2, 3, 4, 5, 6. So 6 is the base which we determined, and I would expect to see some conduction there, and there is none. Right? Now what you have to ask yourself is, should there be something there unless the infrared light is shining within the device? Well, we can soon do that by putting some current through the device and see if it turns on, can't we? That's the only way of testing that. I can't remember offhand. Usually the opto is buried away somewhere behind the network connected to a PWM management chip. It's not right in the firing line like this, so I'm not sure at the moment, but I can't get any conductivity on this thing. We're on diode forward voltage drop. There's no conductivity between any of the pins. So I think what we should do is just tack a resistor on there. And between pins 1 and 2, which is that one and that one, tack a power supply in series with a resistor across 1 and 2, and then see whether this thing actually starts to conduct when we put a little bit of current through the optodiode, through the optical channel. So what can we do about that? Let's get a couple of little bits of wire from the rack, turn soldering iron on. Nothing like fixing battery chargers in the morning instead of doing your proper design work. We're in lockdown after all, there's no one to check on me because I'm the boss. Actually, if I plug the mains into the soldering iron, it's going to help. Right, the weller is now warming. Got a warm weller, and we've got a couple of bits of wire. So we're going to stimulate this diode, get it to do our bidding. It's going to be our bitch for the morning, and we're going to drive it in an orthodox way, but it'll work. All right. So 2 wires, a soldering iron, a prayer, a bit of flux. All I need now is the wife to come back from walking the dog, and I'll have a cup of tea as well. Life doesn't get any better than this. No, we haven't got an au pair, in case you're thinking. Where's my bloody solder gone? Do you know what? I went down to fix some central heating for someone. It was a heat recovery system, and their control board had blown up. Little controller, they charge 150 quid for this controller, and it's just a power supply and it powers up. And I think I've left my solder down there. I'm going to have to use this horrible stuff. Excuse me for this. If you get clouds of smoke and big globbits of solder, don't judge me, alright? And you know I'm a sad old man with a flux fixation, so we're going to have a little bit of flux on there just to make it all super shiny like it used to be in the old days. So anyway, right, so I've tinned my wires, I'm going to tack them on. You might think, well, this is alright, why don't you just you know, just change those bits, turn it on, see if it works, and then change that bit, see if it works. Well, do you know what the answer to that is? I bet you do. If you just change those bits, turn it on, see if it works, guess what happens? It just goes bang again. So you really gotta do the job. Gotta do a proper job. Right, so we want the power supply, we need to turn it on. Sorry about the whirring noise. This is a real sledgehammer precision DC power supply to provide power for a LED. I mean, it's obviously not sensible. So we're talking about, we want to set it to 1.2 volts at the moment. 2 volts. That's something like 20 milliamps. Now, when you connect one of these power supplies, you do have to be a bit careful because they have got an output capacitor on them which is charged. And if you suddenly dump this into a small device, expecting the constant current thing to kick in straight away, you'll get a blip of overcurrent, a little blip, and that little blip will fry things. So you have to put it below its junction voltage and then wind it up slowly with the control, and then you can see the current start coming out 5-10 milliamps, stop, and then you can then make our measurements, see if we've got conductivity on that photo and the transistor. So pin 1 and pin 2, pin 1 and pin 2. Pin 1 is positive, which is this one. Goes on the red clip. For Christ's sake, if it would stay on the bloody red clip, it'd be nice. Someone stood on the red clip, and then the negative goes on the black clip. Someone stood on the black clip and all. Must have gone straight out. It's like one of those dogs with a jaw that's all skew-if on it. Look. Wonder if it would woof with a lisp. What do you think? Comments below. Get down there, you Right, so that's that connected up. And we have a princely current of 0 flowing at the moment, but then we haven't turned the output on yet. So turn the output on. 1.20 volts, 0.12 amp. So there is a current of 0.12 amps, so it's 12 milliamps flowing at 1.2 volts, which I find surprising, across the photo transistor, which is going to be pins 4 and 5. I'm going to get some decent clips. Why do they always sell crap, these people? I stripped her boots off, look. And she's obviously, not only has she been stood on, she's obviously been wet on as well. I obviously had a particularly exciting piece of electronics going on that day, didn't I? Right, so let's try across that pins 4 and 5. We're looking at pins 4 and 5. 4 and 5. 1, 2, 3, 4, 5. Doesn't seem to be conducting, does it? Which is annoying because it's interfering with our plans. which is going to be annoying. Now we still want no conductivity. Yeah, I think the secondary side is conducting power away from our little circuit. So let's just turn the output off, and let's just, there's two resistors feeding down through there. Let's just remove these two paths here. Remind me to put these back on. These have been epoxied on the bloody board again. There we go. They've been epoxied on, they're stuck on with a little red dot of epoxy, these things. Okay, so what's that done to the current? Has that killed the current? Yeah, that's killed current, and we've got 1.4 volts. So let's see if the photo dye is actually doing anything now. Nothing at all. So look at the spec of this device, shall we? It's a CNY17-2. Okay, so this thing can take 60 milliamps, as you can see. Surge current of 3 milliamps. Input side. Power dissipation. Doesn't tell you what the forward voltage drop is, does it? Reverse voltage, power output, collector breakdown, collector power. So it can take quite a lot of current, you know, isn't it? Just so it's driven by little photons bombing down onto the P junction area. Creepage, electric current. Forward voltage 1.25 to 1.65 volts. Right, okay. So we've got at the moment 1.4 volts flowing at 99 milliamps. Input side 60 milliamps, so I should go 60 milliamps. Right, so now we've got 60 milliamps, 1.341 volts, and on the secondary side we've got nothing, not a sausage. No conductivity at all. Let's just put that on ohms to see if there's actually anything there at all. Oh, I think the optocoupler's gone. So the optocoupler needs changing as well, which is a pain, isn't it? I've got to find one of those. So let's just put that back on, turn that off. It is working. The diode side's okay. The transistor side has been fried. As I say, it was directly in the firing line. Time to put the resistor back on that we took off. Bloody nasty solder this. Come on, get in the right position. There we go. So that's that resistor put back on. Right, so we've got the opto isolator changed. So I think we know now exactly what we've got to change, don't we? We've got this transistor down here is gone. We've got the opto isolator is gone. We've got R21 is gone. D14, Z1, T4, and T3. T3 are okay. Is that T3 up there? I can't remember which one it is. Yeah. Yeah, they're okay. Right, so that's what we've got to do. So that's the remainder of the stuff that we have got to chop out of this bloody thing, right? Let's get rid of the vice. I think some coffee is in order. The wife is back from the walk. The coffee hasn't arrived. There's going to be an inquisition. I'll lose, of course I will. Right. And some soldering. You can see these current limiting resistors are way. Right, you got that. There it is. There's the beauty. Now tweezers. Yeah, this FET look. You can't really get the screw out because the transformer's in the way. You could get pliers and start manhandling that around, but that's going to be an issue, isn't it? Doing that by hand. The only problem is that it depends on how much space they've left on here. Desoldering these can be difficult to get them work them loose, so we'll try, and then we'll suck out the hills here. But it may be easy to work that screw out with a pair of pliers without damaging this thermistor. There's a thermistor strapped to the transformer for overheating. You see, so it goes into, gets too hot, it shuts down. Don't tell anyone. I suspect it gets too hot during operation, not just in a fault condition. Yeah, NTC3, you can see it down there, look. I really need to take that out, But I could solder the shunts on this side, the actual sensing resistors. They're only 1/4 watt, but it would be kind of interesting to see them, wouldn't it? Yeah, I'm going to do it in a two-step process. I'm going to get my little pliers and just see whether I can work this screw. Dirty rotten screw out of the hole. You know, when I was 16, I got whisked off from my O-levels, straight GCSEs actually, and I just wanted to get some money and get out of the house because it was a bit stifling, and went to work in the aircraft instrumentation factory. You get to buy your own tools, and I bought these. These are mine from when I was 16, which is 40 odd years ago, 45 years ago. 45 years ago these are, look, and they're still going strong. And I think they were about £2.50. They're CK, made in Swaziland. Can you see that? Can you see it? What's the matter with this bloody camera? Made in Germany, right? So I don't know whether this is going to let me work it out or not. Of course, constipated mathematicians work it out with a pencil, but I'm working it out with a pair of pliers because I'm an engineer. She's coming. Of course, when I take this heatsink out, I can put this all back together and stick it in as one thing. It's 3 less legs to worry about. I have trouble with 2 legs most of the time, especially after a few beers. But you know how it is. I am not a human tripod, unfortunately, so I have to mustn't drink sitting down because you can't tell how drunk I am. Comes the dog, straight from the woods, straight onto the settee. She's presumably had some form of wash, but a rudimentary one. More of a tarts wash, I think. A quick lick and a promise. Actually, I never really understood that, have you? Lick and a promise. The Americans watching this are going, what the hell's he talking about? Hey, there's a nut on the back. There's me ranting away here. And I'm looking after me nut. Can you see it in there? Behind there, they have quite helpfully, I suppose it's helpful, is it? I don't know. Put a nut on there. You stupid people. Clearly you never expect anything to be bloody repaired. There's my screw. There's my anti-shake proof washer. There's the insulator. And where's the nut gone? The nut's still tucked down in there. There's a nut. Right, there we are. So there's me. My accoutrements have now been removed. So we don't need to take the fat out now. We can just concentrate on removing this heatsink by soldering or desoldering. Are we on auto here? Okay, so look, here we are. Got to take that, undo that, undo that. So where's the soldier sucker gone? There she is. She's all primed and ready to go. Oh. So what we're going to do is, it's going to, assuming they've used unleaded solder in this, we're going to put a bit of leaded on to make things go with the flow. And as you know, things go better with flux. Just remember, if you take anything away from this channel, things do go better with flux. So let's give her a bit of a suck. Hey, look! The red light is on and the coffee has arrived. How about that? Well, we'll try and break it loose, shall we? Plenty of heat on there from our 90 watt Weller soldering iron. Little bit of lead to go with the flow. And then might work. Stranger things have happened. So grab hold of the pin, give it a bit of a wiggle. When you're yanking these things out, you have to make sure some daft designer hasn't connected something through here through a through-plated hole to the other side. Because if you rip out the via, you could be in trouble. Oh look, it came out. There we are. So there's our sill pad thing. There, and I'm not sure why they've used the sill pad on that. It's supposed to be W insulated, I guess, but in theory, yeah, it's not an it might be an insulated gate. And there's our two resistors there. One a bit curious actually, if you look down in there, can you see down in there the resistor? There's our 1.3 ohm resistor. Looks like brown orange. So I'd say that was 1.3, although there isn't a 1.3 on the diagram, but they've fiddled about with it, haven't they, obviously? Trying to get the thing right. They've obviously changed the values from when it was originally designed. And then a weird looking thing inside a sleeve. There's an RH tube. What is that? What is that device with a rubber booty around it? Can you see it down there? There's the two shunt resistors, the two current sensor resistors. According to the diagram, it's 1 ohm and 2.7 ohms. Well, there's 1.3 ohms, brown, orange, black, silver. So silver's a multiplier, and we all know that, 1%. And then this thing, both of which are at the moment open circuit. So at the moment we don't know the correct value of this thing unless there's something indicating on it. Can you see it down there, this thing? Unless there's something indicating on it what it is, which is annoying, pretty annoying, but par for the course. So let's get them out and see if we can see what they are, because they're both open circuit at the moment. They've both been blown by this lovely design. Maybe that's what it is. Maybe they say, right, we want a power supply that works for a year, but when it blows up, it absolutely, completely self-destructs itself and puts it beyond economical repair. But they underestimate us, don't they? Well, as soon as you've seen this guide, if you've got a soldering iron and a multimeter, you can fix your own. And you can cock a snoop at the manufacturers. Perhaps they can keep it going forever and ever. There we go, that's gone down the hole. I'm heating it up here and just pushing the wires down through the board so it's standing proud on the other side. I'd normally, if you weren't watching, I would put the components on this side, but clearly the components on the schematic aren't the actual values. You have to watch out for that. They very rarely are, you know, because they've had various issues throughout production, you know, in terms of reliability or tolerance components or something, or some fault showing up in the field, and they update the circuit diagram. And the factory gets all the change notices, and the boards are up issued, and the drawings and the circuit diagrams are up issued, but they never, the only circuit diagrams we ever get to see, the ones that are leaked out through various people that aren't supposed to show them to anybody. So that's the problem. That's your problem, is them not releasing the service information. Should be a legal requirement. Because you think if they do release the service engineer information, it provides jobs for people to do, basically. Too ambitious, eh? Just get hold of the end of it with the pliers, heat up the other side, and she should come out with a bit of luck. That's one. It's annoying about the photocoupler being blown up. I don't think I've ever come across. I've repaired hundreds of power supplies, so I can't remember ever having to change a photocoupler before. But that's what you pay. I'm guessing that I've got hundreds of them in old scrap power supplies. I imagine they're pretty much a generic part with the same pin out. Alright, okay, so there's the two devices out. The two blown devices. And as I say, this one should be a 1.3, because you've got 13 with a 10 divide by 10 silver stripe multiplier. See that? That's 1.3 ohms. Just take my word for it, I'm not lying. Yeah, open circuit. Open circuit. What's interesting about this one, that's another slurp of iced coffee. What's quite interesting is And if I zoom in on that, look, there isn't much indication that that is blown, is it? There's a little speck of paint blown off there, I think, or is that a bit of black overspill? But looking at that, there's no visible indication that that has had a traumatic experience, and yet it is open circuit. So check your current sensing resistors. Some more of that story. Now this one is RH tube. Any idea what an RH tube is? Looks like it's got a resistor inside, so there's no value. But why would they have put an insulator on there? Why would they put a piece of heat shrink tubing on it? Anybody know? Let's take our stockings off now. Oh, fortunately, look, we've got a little resistor inside, so we can work out the value of this one. Should be. Wonder why they've done that. Bit of track on there or something that could short out or something, or I don't know. Right, so this one, where are we? Again, oh yeah, you can see that that one's blown. You can see the lacquer is blown off, cracked open. You see that there? Bit of cracky going on there. Pull her. This one's a keeper. Yeah, pull her scab off there. Look, see, she's scabbed up. Anyway, before we pull any more off, we got brown, black, silver. So it's 1110 divided by 10% is 1.1. So we need to find a 1.1 ohm resistor and a 1.3. Right. Alright, okay. And then the other transistor on here that was buggered, which got to change, was this one, wasn't it? T10. So T10's got to go T10 and R102. R102 to 102's gone. R100. R21 was gone as well. So we've got to take R21 off, which is that one there. So let's just pop that off. Don't forget that these resistors are glued on by a little blob of epoxy. I know I keep on about this, but you'll try and solder and it won't move. But you have to, if you're going to push it, you've got to make sure that it's molten on both sides. Otherwise, you'll damage the tracks, rather than just cracking off. I normally just go get plenty of heat in there, give it a little tweak like that, and it comes off. All right. So be warned. If you think if your solder's not molten, and you give it a good tweak, it could damage the tracks and pull the tracks off with it. Alright, so I'm going to break off now and try and find some components. Yeah, I've done the sums, 1.3 plus 1.1, or in parallel. Okay, I've done some maths using Ohm's law, and I've discovered that two 1.5s and a 2.7 ohm resistors will go together to make 0.5865 ohm resistor, and the two that are in there, if they're in tolerance, give us a resistance of 0.595. So we've got like a 2% error, but that's within the realms of confidence. These have been adjusted all over the place, no doubt, during manufacturing. So let's put those in now. Let's put those back in so that we can get this bloody thing fixed. Of course, I'm only doing this so that other people with the CTEKs can hopefully find it useful, and if they do find it useful, they might be able to fix their own, because I no doubt others have blown up. I looked on eBay yesterday, there was 3 3600s. This one, yeah, MX 3600s for sale, faulty. One of them was only, well, the bidder got to £3. I don't know how far it's going to go. Oh, I sucked 2 holes out at once. Impresario. Professional performance, that is. Sort of thing you see. I was going to say sort of thing you see in a bar in Thailand, but I've never been to Thailand, but I've only Now, from what my sister told me. Right, so 2 of these need to go piggyback, don't they? Is there room in there for piggybacking? I think there is. Oh, I see why the insulation's been put around that one resistor, because it is right next in there. You can see that position of R9 is right next to the metalwork, so that insulation's to stop it arcing over onto the metalwork. So I think we're going to do the same. So let's just put these 2 on here. These resistors are 8¾ watt. Anyway, there's 3 of them, so they're roughly sharing, well, 2 of them are sharing the majority of the power. Actual RMS current on these will be pretty low really, but the peak current will be quite high. And of course you have to take it, if you take the average current going through these, you'd think, oh, it's fine, but it's actually I squared R, so the dissipation of resistor goes up with the square of the current. Okay, do the math. So what you actually happen is that you can get an average current. If it's not an RMS current you're reading, the average current can be, well, that's quite safe. And you think, well, why the hell's that bloody resistor's getting hot? It's because it's not, it's I squared R, so you have to measure the RMS current. And of course a lot of these RMS meters, especially in things which are working at hundreds of kilohertz, don't have the bandwidth to actually resolve that. So you put your RMS meter on and it doesn't see the high frequency content of what's going through the resistor, and you're still scratching your head because your measurement's wrong. They clip a few engineers around their ears when I was a design manager, because they'd been at university and everything and they didn't understand Ohm's law or the power dissipation in a resistive load depending on the form factor of the current. It's quite striking actually when you get into development. You know the theory, but when you start taking the measurements, things don't really do what they appear they should do. And you have to sit and think, and then you have to sit and think about your measurement technique. And as soon as you have a bit of think about it, you think, oh, that's what's happening there. But it can take a while to actually work out what's going on, and it's quite confusing. Right, I'm going to leave that one standing up slightly because it's too long. It's too long, so we're just going to have that slightly standing up in the socket. Snip her off. Right, that's one shunt resistor in place. Let's just bend it up so it's not pushing against the capacitor. Right, there's a good gap there. It's not pushing against the insulation of the capacitor. It won't wear through. It's not near the inductor either. So I'm happy with the position of that in there. Now we've got to put this one in, and I suppose we ought to put a bit of sleeving around it, because obviously they discovered that there wasn't enough creep space. Use this. I can't bother to put the can't be bothered to put the hot air jobby when you're on. There you go. Sleeved resistor. It'll help to keep it cool, won't it? Not. Stuff it back in through the heels. Okay, so that's the current sense resistors reinstated. Now we've got to remove this, let's chop that off. I'm going to give this board a good clean later on with the old isopropyl alcohol. Now, what we got under here, we've got our, this thing is blown. We might as well just snip the wires, and we might as well just give it a bit of a clip. Got to change it. It's blown. We know it's blown. Rare for one of these to be in the firing line, but when it is, you're in trouble, basically. Let's get those out. You see that? I'm going to put a bit of my favourite. Right, so now if I've cut 2 legs, and I should be able to get the other ones out, let's just hook these buggers out. I have to dig around in the junk box and rescue one of these out of another power supply, I think. Alright, pull our little legs apart. Alright, there she goes. The opto isolator has left left the board. Sucky. See, I did it. If I put a little bit of lead in on here, look, if I reflow that, a bit more solder through the hole to actually make it conduct the heat through the whole hole, and the whole lot become nicely molten. Get a nice clean suck on it. Famous last words. What's the matter with this thing? There we are. Right. So that's gone. We'll give it some of the old jollop later. And what was the other transistor that was gone? It was that one there. That transistor there is gone. So again, I'm going to put a bit of the flux on, fluxy flux on there. I've got to get on, I've got work to do. I've got my VAT return to do. So I've got to go and make a short prayer for guidance and resistance of sin in terms of falsifying the VAT return, which is not allowed. And once I'm emotionally and spiritually revved up, I can then go off and pay my taxes. That's everything, isn't it? Take a little drop of this on there. A wee dram before you go. That'll do for now, I think. Yeah, still a bit fluxy, if you ask me. But we don't want to go too clean with this, because what we're going to do next will make her all dirty again. Right, I'm just going to suck off this extra solder on here. It's got a bit of hoovering going on. So my solder joint's not that good there, is it? It's just bloody solder. Here we are. That's lovely. Yeah, that one, I might just give that one a bit more. They are, so my shunts are all in, my shunt current sensor resistors are all in position. So this if you've got this wick, it's bloody good, and some of them it's complete rubbish. If you get some that doesn't work, you think, well, that's bloody useless, it's not working. It's because probably two reasons really. One, it could be inferior, it's just plain crap, you bought Chinese. Two, that it's been left open to the air, and at the office I tell them to keep the stock of this in a bag, sealed polythene bag, with some silica gel, desiccant in there to keep the flux in good condition. Because if you leave this open, and sometimes when you find they're out on the bench like that, this piece that's been outside the pack on the other type with the kind of slide in the big rolls, you find that this bit doesn't work properly. But if you just put a little bit of the old Kingbow or another flux on it, it'll resurrect it. So keep it dry and put it in a bag if you value your stuff. And look at this, I mean, it's like could start a jumbo jet, this would. Look at the capillary action on that. It's lovely, isn't it? Absolutely bloody lovely. There we are. And down here as well we need to do it. Of course, if your iron is no good, you won't have any joy with this, because the copper will just leach away the temperature from the iron, and if it's not coupled properly to the element won't be able to replenish the lost thermal energy. But we're going to go and hoover everything up so we can solder everything back on, basically. I will do this with an iron. I'd normally just put some solder on, some flux, and then put them all on there and melt the whole bloody lot in one go. But that's not really helping you, is it? Get rid of some of this epoxy. It does melt this stuff. Our chip can sit down properly. And you can use this like a little wire scrubber, like a piece of, like a Brillo pad really. High temperature Brillo pad. That's what it is. Just to polish things up a little bit. There's a little bit of solder there. Anything else? Now, according to me, if we just repopulate this board, obviously the FET, yes, the FET. Why don't you tell me? The FET. Come on. Let's take the 3-pin shorting link out. This is the root cause. This is patient 0, the zombie apocalypse that is this board. Yeah, it's just like it had its own pandemic of over voltage going through the board. And there she is, look, standing upright, proud. Oh, IRF 830A, is that the one that's on the circuit diagram? Probably. Right. Do you know it's locked down at the moment, and yeah, my wife is a very active lady. She can't go to work in the museum. That's why she married me, because she likes working in the museum. So she can't she can't go to work in the museum. She can't go to the gym, which she does all the time. She can go cycling, which she does, and she does aerobics and yoganuary. They all in January. There's veganuary, which is don't eat any meat in January, and there's yoganuary, which is a daily yoga things. And it started off quite normal. And there was just like a bit of flopping and a bit of groaning going on in the sitting room. She rolls up the carpet and off it goes. And then I'm not allowed around for hours because I'm not allowed to see what's going on. And what's the date today? It's the 27th, I think. And yeah, she's doing bloody handstands against my office door. She says, "Don't come in for a second, or don't come out." And there's this flopping and banging going around there. There's a fight going on in the living room. And it's my wife doing headstands and handstands against my office door. Which is fine, but not when you're trying to record something on the video. It sounds like someone trying to break in through the door, having a fight in the living room. So anyway, what I thought I'd do is the garden. Last year the garden had a hell of a going over because there was nothing else to do and the weather was nice. So all the hedges got trimmed and everything got done. And then we put a patio down. But this time I thought, to keep her busy and out of the house, I bought her a skip. Now, if you said to a woman, "I bought you a skip," you'd duck, wouldn't you? Because of the onslaught that would be launched against you straight away. But no, it's she loves a skip. I do have to go out every night and fish all my stuff out of it, but it's like recycling. It's a home recycling. I recycle the stuff back into storage, and I suppose I have to put it away, but she's doing the garden at the moment like a woman possessed. So yeah, if your wife's unhappy and you've got space, get her a skip. Because I don't know if the Americans know what they call it, a dumpster in America, I think. In the UK we call it well, we call some people dumpsters as well, but for different reasons. Not reasons I can go into at the moment, because I'll probably get cancelled. Right then, okay. So the FET is gone. There's no signs of exploding on that FET, is there? As they do. Right then. Now I reckon if we stuff all that stuff back on, we're going to have a runner there. Don't think anything else is blown up. Pastas look good, don't they? Everything else looks good. So that's this one. MOSFET IRF A30 PBF, which is this one. I'm handling it, but I took it out of the packet and I'm earthed. Yep, and that's the Farnell part number 8648549. So you get this from Farnell. And then what was this? This is the 4000 low CMOS 4069 chip. 14-pin SMD, that's the part number. I've got a packet of 5 and they're about 3p each or something stupid like that. So they really are just as cheap as chips. Mind you, they've been going since the 60s, late 60s probably. So this, where's my nut and my washer? This can be screwed back together, can't it? Stick that on there. Stick that on there. Put my screw through the heel. top hat washer. Okay, lock washer, nut. Nuts on. Right, okay, so let's just tighten that up. Now if you tighten these things up too much, then these corners can force through this and break through the insulation. It's not such a problem on this, but it has to be double insulated by law to pass the safety regulations. You have to have something insulating it from that, and then something insulating that from the outside, and insulating that from the outside is the case, okay? So double insulated. Right, quite often you'd have a plastic body fet there without the metalwork. Not quite as good heat dissipation, but they are double insulated because you've got an insulated body fet, a whole plastic package, rather than the metal tab onto which the wafer is mounted. Alright, anything else in there that need looking at? I suppose I ought to check the snubber diode while I'm here. Yes, let's do that. I don't think it will be blown for the reasons we discussed earlier, but you'll have to bear in mind with the readings because I can't display this meter and I'm in a hurry now. So that side there we should get conductivity. We've got 600 millivolts in that direction. Look. Can you see that? Can you see that? But you can't see that, can you? It's awful, isn't it? I'll have to read it out to you. Trust me, I'm not going to lie. 604 direction, 606, and in the other direction, which is reverse bias, there's nothing. That diode has survived. Alright, well, there you go. So she's sitting lined up. Pin 1's at the right end. A little bit of old solder, especially this crappy old solder. Let's go and find my other roll of solder. I haven't thrown it away. It's a bit odd that it's not here. It's going to be tricky this, but I'll do it. Right, so you've got a clean tip. And what you do is you put a blob of solder on your tip and then just heat the pad. And you can see it flows onto the chip without touching the chip. Alright, and that's the name of the game, is to solder these pins without touching the chip. Obviously once you've done the first one, you've got an anchor there, so you should be alright. And then these two are connected together anyway, so it doesn't matter. There's those two are connected together. Do you remember those 3 bridged stages of this chip? Then we go around the back, reach around the back with a degree of care. Alright, so that's that chip soldered. We'll clean it all up later. So now, we need a bunch of resistors, don't we? Should we do the resistors first and then the transistors? Yeah, let's do that. You notice how it's all high value ones that are left. So we're looking for R10, the 1K 0603, or yeah, 1K 0603. So we get the resistor book out. Right, what's the first thing? There's some trouble with magnifying bloody glasses, you know. They're not 0603, they're 805s. Let's put 1Ks back into the 0603 book. I got these resistor books, they're about 20 quid each, 1%, full of all the different values, and they're very useful actually. Very, very quick to get your hands on the resistors, all nicely organised on the shelf in the form of a book. And away you go. Resistors in the book, happiness. Oh, happiness maintained, resistors all over the place, unhappiness, chaos, 1K. These are Yagos. No go goes like a Yago goes. Like the Borg say, resistance is futile, but actually resistance is quite good. What we're doing, I've forgotten which resistor, resistor 21, 1K going on. There we are. Far too good a resistor for this. It's going, what's going on? We've got 1% resistors. Okay, R21 is on. What else have we got missing? We've got R102. R102 is a 1K as well. Okay, another one. R102, 1K going on. Probably started out as a 2 amp battery charger. It's been just modified. I think Rolls-Royce did that, didn't they? And they fell foul of a jet engine with turbine. What was it? CFM. One of them, anyway. They decided scaled up the thing and didn't test it properly, and of course, turbine blades were breaking right, left, and centre because they just boosted the power by scaling things up, and it doesn't work. And it certainly doesn't work in switch mode power supplies in terms of reliability. R100. Come on, baby, clean your tip. I suppose I've got to use it up in the interest of the environment. Getting the hang of it though, eh? 22k to ground on that line. Yeah, you look at where R5 is on the circuit. You think, rather than being a jack of all trades and master of none, you'd think someone would design a really reliable power supply module which could be licensed out like ARM or whatever. Because most of these design engineers woke up one day and thought they were an engineer. Of course, you know, you wouldn't want these guys designing something like a, what, I don't know, chairlift cable maybe? Would you buy a chairlift cable off this designer? I wouldn't even get anywhere near it, let alone an airplane or a heart monitor. All because the FET wasn't properly protected. So did the FET die of natural causes, or was it murdered? I think things like Fairchild and Infineons, or on semi FETs and IRF especially, they don't die of natural causes. It's homicide, or not homicide, chipicide or resisticide by the designer. I'm going to get shot now, but I've had Panasonic TVs the last 30 years and I've not had a single fault on any of them. And we've got 3 in the house at the moment. And yeah, 2 main watching TVs, and I've not had a single fault on a Panasonic set. And when I used to go to Rediffusion, do you remember the old when everyone used to hire their TV sets? Well, all the old TV sets used to end up in a big warehouse in Edmonton around the North Circular, near where IKEA is if you're in the UK. And we used to go there, and there was these sets all piled up, and there was Philips and Bush sets, the G11 chassis, and we mostly G11s actually, ones with the 8 push buttons on the front. Was it 6? 6 probably. And yeah, the Philips sets would all be piled up, but in the main part of the building you walked in, there was all Mitsubishis and Sony sets which were ex-rental, and they were all still working. The nice picture on, you know, a bit faded maybe, but yeah, all the Japanese stuff was working, and all the stuff that was designed in Europe, like the Philips and the GEC and the and they were all badged, weren't they, anyway, but Dynatron, you know, the expensive ones are all screwed, you know, power supply faults and resistors, capacitors, transistors blown, tubes all knackered, you know. And we used to go through with a tube tester and test all the tubes and swap all the panels out, and then buy the sets for £5 each, take them back and then refurbish them. But yeah, reliability. So it is possible, because these, you know, some manufacturers seem to get things totally reliable, very rarely fail. Others just don't, do they? Let's face it. So we've got T10 and T2, and that's it, isn't it? T10, T2, and then the Octo. We put R13 back on. Okay, yeah, so I've got some transistors here. They're just general purpose. Well, they're not general, but actually a bit better than general purpose. But you know, in these situations, the transistors are just, whether the HFE is 40, 50, or 100, there's not much difference at all, really. So this is the PMP one, the J1Y, and that goes in T10. I'm guessing I'm going to have to check that thermistor to make sure that hasn't gone kafooey either. Might have done, mightn't it? And then T2 is the inhibitor, the one that turns off. Interestingly, when you might not realise this, you probably do, so if I'm teaching you something you don't know, when you think of the emitter base collector, the emitter goes to ground and the collector goes to the positive rail, say in the case of an NPN transistor. When you turn the transistor fully on, you drive, you know, obviously not a dangerous current, but if you fully saturate the transistor, then you still got the 0.6 volt roughly. Obviously it increases the more the current, but generally speaking, you've got the 0.6 volt emitter base, or base emitter junction voltage. So you've got 0.6 volts across there. but if you measure the transistor, the collector emitter junction is about 0.1, 0.2, 0.12, something like that. So in effect, when you drive a transistor really hard, the collector base emitter is reverse biased by up to a half a volt. So the collector will be half a volt lower than the base. Did you know that? Probably you did. I didn't find out until I was about 30, I think. I was a late developer. Alright, so we're fully populated except for this 6-pin single channel opto isolator. Do I have any around? Alright, so I've had my lunch and I put my brown trousers on. Now I had a good look at everything on here now after I finished soldering. I had to find, I got a 4-pin opto isolator because I couldn't find the 6-pin, and just put it in so that the connections matched up. But basically had to put it in on the skew. Can you see that? Okay, I need to tidy that up actually and give it a clean. But that's where we are at the moment, and it's looking pretty scrappy. Needs a damn good clean. But first of all, brown trousers are on. Now, oh yeah, the mains is connected. I've just soldered a couple of mains wires into here, connected into this, which is connected to the mains, through an isolation transformer, so I can touch this without getting a shock if I'm grounded or something. And my scope probe can work. I've explained this before. And it's also through a 100-watt light bulb. So if there's a short on here, my bulb lights up rather than a big bang. So, drum roll. Actually, I actually checked. That switch looks corroded to me. That switch looks corroded to me. Let's just see if it works. Yeah, it is 2-volt switch. So let's put that to there. That to there. Press the button. Nice. Switch is knackered. So, vernier measure. We have a stem height of 5.5 millimeters. What have we got that's got a stem height of 5.5 millimeters? I wonder if one of my boards is 5.5 millimeters. Here's one of my Bluetooth boards I invented. 6.85 millimeters. 6.93, there's 7 mil then, those switches. 5.5 to 7. There should be like a button titty thing goes on top of there. Well, I bet we haven't got that. Where's the case for this thing? No, look, there's just an ordinary membrane that pushes down. So there's supposed to be a little wim-wam goes on top of there, which is not present. I don't think I ever had it. So let's face it, a 7 mil one might work, won't it? Mightn't it? Yeah, look, I've got a bag of these. That's about right. What have we got on this? We ask ourselves. 6.86. So it's really 7 mil again, aren't they? We're going to have to shave a bit off the top of her if she's too long. We'll deal with it later if it's a problem by snipping a bit off or something. 1.5 mil too long, but I don't know how long that little disc that normally sits on the top is. Out the old. Jollop. I got VAT returns to do. It's the end of January. Still, I've got all night. I like to do things like VAT returns when I'm feeling really weary. Then I don't really notice how fucking boring it is. I just wake up at 3 in the morning and think, oh, that's about done it. Right, it's got a different mounting pattern on these legs. Let's just tack one on the right place. scooting it about backwards and forwards like a bloody horse drawers. Well, look, that allows us to test it, won't it? Let's solder support it. It's in sparrow shit soldering today because I don't have my normal solder with me. Right, so now, can you hear that? Switch is good, switch is good. Right, I've tried to put this off as long as possible and I cannot put it off any longer. Alright, so we're going to turn this on. Going to stuff some of Her Majesty's volts up her shirt. And here we go, ready? Oh look, lights on. Thought I was going crazy there. So let's turn the exposure down. Right, so you can see the one light, the power light is on. So we've got power. So if we just check on the reservoir smoothing capacitor, which must be, I can touch this end, don't forget, because I'm isolated from, that's the bad end. That's the spoil your day end. Where are we? There it is, there's a capacitor down there. So it is those pins there. And you'll have to bear, well, I'll show you now the light's off, can't I? I think. No, you can't really. I'll turn it around that way. There we are. So where are we on the supply? 12 volt battery charger, expect something like 12, 15 volts, something like that. See there? The volts on. More volts, Igor, and 14.52. Right, so the power supply is running. It is working. It is correct. Okay. So if you just follow if you just follow that simple, let's just press the button. Oh look, different modes work as well. Nothing going on up here, but then there's no battery connected. I'll put the leads on. If there's any issues with this side of it, I'll come back to it and show you. But otherwise, assume that at the moment it's fixed. But it is working, and yep, everything. The lights are on, and it's at home. It's a done deal. I'm just going to give it a good clean. But if you've got one of these and you just follow those rules, I mean, basically, it's just go probe around using a simple standard procedure. Looking at the circuit diagram, you should be able to fix it, let's face it. And if you need some bits, I can get some posted out. I'm very, it's cost the postage per quid for the components or something like that. I don't want to get into a mass posting session, but if you've got a problem, then leave a note. And you've got to be a bit self-starting though. I'm not going to say, oh, my battery charger's not wrong, what's wrong with it? You're going to have to get your meter out, get your hands dirty, get your brain engaged, and make a few measurements. But I hope you enjoyed watching that. And then if you look down there, there's a subscribe button which you can hit if you're not already subscribed. If you are, thanks very much. And leave me a like if you can. And that concludes the repair of the CTEK multi xs3600 power supply fault, which is where they mostly fail. Alright, job done. Alright, so I got an opto-isolator out of a different power supply. The pin out was different. It's only just hasn't got the base connection of the virtual base connection of the actual transistor, photo transistor, and the pins are different, so I've had to mount it in slightly differently, but otherwise it's just the same. Okay, so pins 1 and 2, and then 3 and 4 become 4 and 5 basically. So that's incorrectly. So I'll put the leads, put a mains lead on it, and brown trouser moment. Hold on.